Thanks for tuning into this Revision Zone Maths video. In this video, we're going to look at how to solve modulus equations and actually how to perform modulus transformations, right? In the previous video, we've already defined what a modulus function is, and we've actually even looked at some basic properties of how to do modulus transformations. So if you're unfamiliar with that, please go back and take a look at the previous video. But in this video, since we don't really need any new theory, the content is going to be basically example heavy, right? So let's take a look at the first example. The first example requires us to prove that the modulus of x is always the same thing as the modulus of negative x, where x is any real number. Now, this is obviously true from just the definition of the modulus function that I gave in the previous video, which was, the modulus function basically throws away the sign, right? Another way of saying that is it just gives you the absolute value of a number, irrespective of whether that number is negative or positive. So it's unsurprising that this is true. But let's take a look at the proof sort of more formally. And what we want to look at is we want to look at the definition. So we know that the modulus of any input is actually defined to be a piecewise function. So it's just going to be the input itself, assuming that the input is actually not negative. And it's going to be negative of the input, assuming that the input is actually itself negative, right? So the idea for this proof is to apply this definition to both the left-hand side and the right-hand side independently, and then to be able to manipulate things to be able to show actually the definition gives us the exact same thing on the right-hand side in both cases. So let's think about the modulus of x. Well, this is obvious because this is the thing we defined in the previous video, but we can just sort of rewrite it here as follows. Now the slightly harder one, not that hard actually, but slightly hard, is the modulus of negative x. So again, I just apply this definition quite literally. So I'm going to have my input, which is going to be negative x, and my input has to be non-negative. And then I'm going to have my input, which is going to be here, but in this case, I'm going to have to make it negative, and of course, my input itself better be negative, right? So from that, we see that actually they're not that far apart, but we need to be able to massage this a little bit more to get it in this form, right? We could massage that to get it in this form, but this is simpler and this is more complicated. So we're going to go from something a bit more complicated to something a little bit more simpler. So the key idea is I want to be able to say, well, if negative x is positive, then that's the same thing as saying x has to be negative. And of course, all I've done here is multiplied through by -1 and used the fact that inequalities actually swap signs, right? So with that, I can come back to my definition of the modulus of negative x function, and I can say, well, I'm going to have this statement here, right? So I've now simplified, in some sense, the first piece of my modulus function. So let's look at the second piece. So if I have x or negative x is actually less than 0, multiplying through by -1 is the same thing as saying x is actually necessarily positive, right? So with that realization, I can come back and say my negative x is such that x has to be strictly positive. And indeed, so now we've got our domains of our pieces being a lot nicer. But this thing here can still be simplified. So I can actually say this is exactly the same thing as negative x, where x is less than or equal to 0, and x, where actually x is bigger than 0, right? Because the two negatives here are going to cancel effectively. So now this is looking a lot more promising because this is looking very much like that. The slight difficulty is we have a small issue with what's happening with the 0. Here, I've got x being more than 0, but here I've got x being less than 0, right? Whereas in the other case, I've got x being less than or equal to 0, and here x being bigger than or equal to 0. So somehow to be able to say this function on the right-hand side in total is the same as this function on the right-hand side in total, I've got to be able to match up their domains as well. So I'm going to use a clever way of just splitting something up. I'm going to say I can come to this first function here, the first piece, and I can split that piece itself into two separate pieces, right? So I'm going to say, obviously the two separate pieces are going to be defined by the same function, but because they're two separate pieces, they're going to have two separate domains. And in the first case, I want to choose the domain to be just x less than 0. And in the second case, I want to choose the domain to be x equals 0. So we now see that collectively these two x inputs are the same as this thing here, right? And of course, the function in both those cases is exactly the same as the function in that case. So I've been able to split up my first piece into two separate pieces, and then the piece, the second piece in the initial case is just going to remain as it actually is. So I'm just going to say I'm going to have x with x being strictly bigger than 0. Now, the beauty of this is as follows, which is, let me write it in red here. X is actually the exact same thing as minus x for x equals 0. So this is a fact. So using this fact, I can come back and say, actually, this thing here can be rewritten as, so now that I actually have this in this form, right, I see that the function here is common. I can actually now combine these domains, right? So I can actually come back and say, in fact, let me just do some space here. So I can say, in fact, the modulus of negative x is the same thing as negative x being strictly less than 0, and then x where x is actually bigger than or equal to 0, right? And so we're basically done, because if you go back to the previous video, I made it quite clear that it actually doesn't matter which order we write our pieces in, right? That's completely up to us. As long as we're not changing the function and we're not changing the domain, we can choose to write this first and then write this second, or we can choose to write this first and write that second. So actually I can just come back and say this thing here is exactly the same thing as, and therefore what we have is we have the modulus of x is the same thing as, using this definition here at the top, is the same thing as x, for x being bigger than or equal to 0, negative x for x being less than 0, is actually the same thing as modulus of negative x, oops, it's the same thing as modulus of negative x by now using this definition here that I've actually figured out, okay, the right hand side in particular. So perhaps I should actually move that to sort of be here, say, right? And this completes the proof. Before moving on to the next example, let's quickly take a look at this remark, which is basically giving us another way to prove the exact same result we just proved. So this is a more geometric way of looking at it. So we can basically start by just getting a graph of y equals mod x, which we know to be as follows. And then we know that if we want to go from mod x to mod of negative x, that's basically the same thing as the transformation of f of x going to f of negative x, where obviously you take your f of x to be your y equals mod x. And what does this transformation actually do? We know that this transformation basically does a reflection of the entire graph about the y-axis, right? But the beauty here is this graph of mod x is already symmetric about the y-axis. So when you actually do a reflection, you end up with the exact same graph, right? So that basically tells us that when you've got mod x being transformed to mod of negative x, right, because the graph is not going to change, you're going to end up with the exact same thing. So this is a much, much easier way of actually proving the exact same result. Let's take a look at the next example. So in this example, we have another quite interesting property, which is actually if you take the square of a modulus function, then you can just drop the modulus signs. Okay, so another way of saying that is squaring basically kills the modulus sign. So let's see a proof of that. Again, this shouldn't really be that surprising. So let's just say for x being, say, bigger than or equal to 0, we know that the modulus of x function is just going to give me x. So actually, when I square the modulus function, it's the same thing as having x squared. So we've proven it for x being bigger than or equal to 0. And then for x actually being less than 0, the modulus of x function is actually going to give me negative x, right? And again, if I square this, then actually I'm going to just get negative x squared, which is the same thing as x squared. So again, we've actually proven that. So that is modulus of x squared is equal to x squared for all x being real numbers. Now it is worth making a couple of remarks here. So one remark might be, actually, we could have done the exact same thing by just doing this. So saying modulus of x is x for x being bigger than or equal to 0, is negative x for x being less than 0, And actually, when I square the mod function, that's the same thing as me effectively, in some sense, squaring each part of my piecewise function, right? So it's going to be negative x squared, and of course this then gives me x squared for x being that, and also x squared for x being that, which effectively just means it's x squared for all x, right? So that's another way of writing this out. I did it this way because I thought that was easier to follow, right? But you should be aware that this sort of thing does happen. And the second thing worth saying is actually we cannot use our transformation of function properties or transformation of function laws here. Why can't we use this? Because if you go back and think about what sort of transformations we were writing down, you will sort of think to yourself and figure out that actually we were writing down linear transformations. And in fact, what we have here is we have something which is squaring something. So that's definitely a non-linear transformation. Okay, so there might be other geometric ways of being able to argue that this property is going to hold without doing any algebra, but you can't use the standard sort of linear transformations that we've seen so far. And in fact, on the A-level syllabus, there's nothing is said at all about non-linear transformation. So you need not even worry about this in the geometric sense. So example 3, we have another interesting property, and this property basically tells us what we do when we're factorizing things inside modulus functions. So in particular, say if you've got two numbers, a and x, and they're being multiplied, and then you're taking the modulus of the whole thing, then what the property basically says, when you actually go to factorize, say, an a out or an x out, you can't just write the a or the x by themselves. What you have to have is you have to have the modulus signs next to them, okay? So when factorizing inside a modulus sign, we must keep the modulus sign. Let's see a proof of this, and I should say there are lots of ways I can now turn in terms of proving this, and I think the easiest way might be actually taking the right-hand side and showing that's actually going to give us the left-hand side when we apply the definition of the modulus function. So let's try and do that. So let's say the modulus of x, and obviously the modulus of a, and we want to be able to apply the modulus function definition to that and to that. So when we do that, we get something like a for a being non-negative and negative a for a being negative. And then we multiply this by the definition of mod x, which is x for x being non-negative and negative x for x being negative. Now here's the slightly tricky part, which is when we actually multiply this out properly, we're actually going to have lots of branches. So I could have a case where a is positive or non-negative, but x is negative. And I could also have a case where a is negative, but x is non-negative. And I can have a case where a is negative and x is negative, or a is non-negative and x is non-negative. So all those cases have to be considered. So in other words, when I'm going to expand this out, what I'm going to get is as follows. So we can either have the a times by the x for both those domain values. So we can have ax where that's the case and that's the case. Or we can have a times by minus x for these respective domain values. So we can have minus ax where that's the case and that's the case. Or we can have negative a times by x for these respective domain values. So again, this is going to give us negative ax where that's the case or that's the case. And lastly, we can have negative a times by negative x for these respective domain values. So we can have negative times negative is going to be positive, so it's just going to be ax, and it's going to be. Now, I would like you to cast your eye on these functions quite carefully, these sort of expressions, and you will see that actually we've got the same thing repeated here, and we've also got the same thing repeated here. So actually, what we can do is we can just rewrite this in a much more simpler version. We can just say our functions are just going to be ax and minus ax, and the only thing we have to worry about are actually going to be our domains. So either I'm going to have both a and x being non-negative, which is from here, or we're going to have both a and x actually being negative, which is from here. Okay, so that's going to be our first piece effectively, and then the second piece is just going to be this thing here, but then with that domain or that domain. So we're going to have, now the thing worth thinking about here is, here we've got same sign for both a and x, and here we've got same sign for both a and x, but here we've got different sign for both a and x, and we've got different sign for both a and x. So in other words, in the second case, if actually we take a look, if a is non-negative, then x is negative. And if a is negative, then x is non-negative, right? Whereas in the other case, a and x both have the same sign. They're both positive in that case, say, and both negative in that case, say. Okay? So in other words, I can actually tidy this up a bit more and say this is the exact same thing as ax, where a and x have same sign, and it's negative ax, where a and x have different sign. This is just so much nicer as a way of writing it out. Okay, but another way of equally writing that is actually to say it's ax where a times x is non-negative, and it's negative ax where a times x is actually negative. The reason why this is the same thing as this thing here is because consider the case. If we have a positive and x positive, and when we multiply them, then ax is going to be positive, right? But if we have a negative and x negative, when we multiply them, well, ax is still going to be positive. You see? So same sign means that condition is actually satisfied. And of course, if the signs are different, and we multiply them, then obviously the thing we're going to end up with is guaranteed to be negative. So in fact, both these conditions are the same as both these conditions, but once we've written this in this form, we notice that this is nothing other than just a definition of the modulus function. Okay, so we've actually been able to do our proof. Example 4 is a nice, easy example, and we have to just be able to sketch this modulus function. There are many ways forward, so I'm just going to say, well, if I know what the formula is for this function, I can graph the function, right? So I apply the definition of the modulus function, so I say I'm just going to have x plus 3 for when x plus 3 actually is non-negative, and I'm going to have negative of x plus 3 when x plus 3 actually happens to be itself negative. But what is this? This is nothing other than just x plus 3 for x actually being bigger than or equal to negative 3, and this is negative x negative 3 for x actually being less than negative 3. So now all we have to do is we have to be able to graph that part for those values of x, and we have to be able to graph this part for those values of x. So we can sort of do that right now, which is we come here and we say, okay, let's get a coordinate system, and then we say let's think about the line maybe in a different color. Let's think about the line y equals x plus 3. So what is that going to look like? That's going to look like something which passes through, say, something like there, and it's going to go up, and it's also going to come all the way down, of course, right? So that's y equals x plus 3. And let's also think about the line y equals minus x minus 3. So that's going to pass through here somewhere, and it's going to go something like this, and it's going to carry on traveling all the way down. And of course, the point at which they're meeting, the green line and the blue line, that is, that point there, is actually minus 3, right? And we can sort of check that. We can say, well, when x equals minus 3, let's think about the green line, y equals x plus 3, which is going to be minus 3 plus 3, which is 0. So that's fine. And in the second case, we're going to have y equals minus x minus 3, but x is obviously minus 3, so we're going to have this, which is the same thing as 3 take away 3, which is of course 0. So indeed, the lines we've drawn so far are actually perfect. Of course, at this stage, it's worth saying that this cannot possibly be the entire graph of our function, and that's because we haven't actually applied these restrictions on the domains, okay? So we come and we apply those restrictions on the domain. So let's have a think. So in the first case, where we've got x plus 3, we actually want x being bigger than -3. So we actually want, for all these x values, we actually want the green graph. Okay, so I'm going to get rid of the green graph for everything else, right? And now for sort of this graph here, we have x values being less than -3, which means for all these x values, we actually want the blue graph. So I can actually get rid of the blue graph for everything else. Okay, and there we have it. So the thing that we have left over is actually exactly what we were after in terms of a graph of our modulus function. Before moving on, it is actually worth making a remark, which is we could have done this another way, right? So the other way we could have done this is we could have said let f of x actually be the modulus function, so mod x, and then we could have noticed that actually if we want the modulus of x plus 3, that's exactly the same as f at x plus 3. And in fact, we can consider a transformation between the two, and we know what that transformation is going to do. We've got basically f of x going to x plus 3, and we know that's the same thing as just a transformation of 3 to the left on the horizontal axis, right? So in that case, because we know that the graph of the modulus of x function, so let me maybe do that here in red. So we arrive at this graph here, which is obviously a standard sort of graph we've seen before. And using this idea, we can actually say that we could get the graph for a mod of x plus 3 just by shifting the red graph entirely to the left by 3 units, right? And we see that this is actually consistent with the graph we drew earlier, okay? So this is another way of being able to sketch the graph of modulus of x plus 3. Example 5. So we have another rather interesting looking modulus function. In fact, it's defined by having two modulus functions being added, and we have to be able to sketch this. And of course, you're given the sketch. So the point of this example isn't actually just to get the sketch, but to really understand how to go from something like that to be able to get the sketch. Okay, so one way of doing it might be just put in as many x values as you might please and get the corresponding y values, get your table, and then to pair up your x values and y values and then plot them and then basically just get this. So that's the slightly rudimentary, not really thinking too much way. The slightly more analytic way is what we're going to do now. So let's have a think. What we're going to do is we're going to want to write the graph of that as a piecewise function, and then once we've got that, we should be able to see that actually we're going to be able to sketch this by hand directly, right? So to be able to do that, we have to be able to expand this in the definition of modulus function and this in the definition of modulus function. So we do that now. So we can have y equals, well, okay, it's going to be x plus 3, and that's going to be for whenever x plus 3 is actually not negative. And then it's going to be minus x plus 3 entirely, and that's whenever x plus 3 is actually negative. And of course, all of that is being added on to the second branch, which is going to be x plus 5 for whenever x plus 5 is actually not negative, and minus of x plus 5 whenever x plus 5 actually happens to be entirely negative. So maybe we can simplify this a little bit. So we can say, the first branch is just going to be x plus 3 for x being bigger than or equal to minus 3, and the second branch of the first part is going to be minus x minus 3 for x just being less than minus 3. And then the other thing is going to be x plus 5 for x being bigger than or equal to -5, and of course minus x minus 5 for x strictly being less than minus 5. So now we have to think about how these branches are actually going to combine, okay? And the thing is, it's the domains that are actually in charge here. So I have to see for which inputs am I going to have which outputs, and then I've got to add them up in the corresponding way. To be able to do that, it's good to maybe have the real number line and just mark out the key points. So we know the key point is going to be at minus 3 because minus 3 is coming here. And we know the other key point is going to be minus 5 because minus 5 is coming here. So let me just mark that here. So I'm going to say minus 5 and I'm going to say minus 3. Let's now just think about this region of the real numbers. Okay, so let me mark that out. So how can I have x being bigger than minus 3? Well, that would do it. That's, x is always bigger than minus 3 in that case. And actually, because I'm going to have to be dealing with the second branch, this branch here would also actually work for us. Because if I come here and say x is always bigger than negative 5 in that branch, then actually we see that there's a huge amount of overlap. So there's a huge amount of overlap here, right? Which means I can actually come back and say, for my full answer, I can actually say I'm going to have x plus 3 plus x plus 5. So let me maybe put brackets around here. And that's going to be true for when x is actually bigger than or equal to minus 3, right? And again, the justification is, as I've actually given here, that this branch is valid on all of that green part, and this branch is valid on all of that, all of this yellow part. So for that red part, you actually have both the green and the yellow overlapping, which means because we're adding each branch, we add the relevant components, okay? We now basically go and repeat this sort of way of thinking for other regions that we actually have, right? So let me just mark out the entire region where x actually happens to be less than negative 3. So this entire region here is where x is basically less than negative 3. And since we're interested, say, in this interval here, we've actually got the blue and also the green actually overlapping, right? So because I've got to add, that's what the function's telling me to do. I'm going to add this part to that part, and I know it's going to be valid between that x value and that x value, okay? So I come and write this out. So I say minus x minus 3, and then I add this to basically x plus 5. And I know this is valid for x basically being bigger than or equal to minus 5, but being strictly less than minus 3. And lastly, we mark the entire region where x is less than minus 5. And we can actually now again see that for this entire region here, we've actually got an overlap between this part of the branch and actually the blue part of the branch here, right? So I'm going to add that thing there to that thing there, and I know it's going to be valid for the entire case here, right? So let me again just sort of write that down. So I'm going to have minus x minus 3 add minus x minus 5, and that's going to be valid for x strictly being less than minus 5. So we've basically been able to write down our function, our initial function, in a form which is nice and piecewise. So perhaps all we need to do is just simplify this, and I can just rewrite that here. So of course, what we're going to have is we're going to have x plus x is actually going to give me 2x, and the 3 plus 5 is going to give me 8. So I'm going to have 2x plus 8, and that's valid for x being bigger than or equals to minus 3. And then for the second part, we're going to have negative x and plus x, so the x's are going to cancel, and I'm going to have 5 take away 3. And of course, 5 take away 3 just gives me 2, and that's going to be valid for x being between minus 5 and minus 3. And lastly, I'm going to have minus x take away x, that's minus 2x, and then minus 3 take away 5 is going to be minus 8. So it's going to give me minus 2x minus 8, and that's going to be valid for x being strictly less than minus 5. And of course, at this stage, we can sort of see what's happening. We see that if we go back to our graph, we see that actually y equals 2 is a key point, or it's actually a key y value, because the function is constant, and it's actually constant entirely for certain x values, and we know what these x values are. That's going to be minus 5, that there is going to be minus 3, and therefore the graph on the top here has to be 2x plus 8, and the graph here has to be minus 2x minus 8. So you can sort of see immediately as to once we've actually got a formula like that, we can just go and plot this or sketch this straight away. So I hope you found this useful. Let's take a look at the next example. Example 6, well, this is a very, very important example. We're given an equation to basically solve, but the equation is not sort of a standard equation. It's actually what's called a modulus equation. In other words, there is at least one modulus symbol somewhere in the equation, right? So off the bat, I should actually say that if you think that you can just get rid of this modulus symbol and just solve this as a linear equation, then actually that's not going to work, right? You can try that, and in the best possible case, you might get one solution which works, but quite frankly, usually there are multiple solutions. So if you don't treat this in the right sort of way, you're going to be missing some solutions. And from the point of view of the A-level exam, This is a standard sort of question that comes up again and again, so you really need to be comfortable with being able to manipulate this sort of thing and solve equations like that. So before we actually jump in and see the techniques for solving this sort of thing, let's take a look at what a solution might look like, or what an answer might look like, okay? So before we look at the answer, let's think about why x equals 0 is not the answer. And the simple reasoning is that when you actually put x equals 0 into here, you find that the left-hand side does not balance with the right-hand side, right? And you can sort of see that here, which is when you put x equals 0, the 2x minus 1 goes to 2 times 0 minus 1, which of course is just minus 1. And the modulus of that is 1, which is definitely not 3, okay? So x equals 0 is not a solution. On the other hand, x equals 2 actually is, and so is x equals minus 1. And you can sort of see that here. So the 2x minus 1, when x is 2, just goes to 2 times 2 minus 1, which is nothing other than 4 minus 1, which is obviously just the modulus of 3. But the modulus of 3 is just 3. So in fact, when you put x equals 2 in, you actually get 3. So the left-hand side and the right-hand side balance, and x equals 2 is a solution. And the exact same thing happens for x equals minus 1. I'll sort of leave you to check the details if you prefer. So let's take a look at how to solve equations like these. And I'm going to go through 3 methods essentially, and they're going to be in a fair bit of detail, right? So the first method is actually a graphical approach. So the idea here is we sketch the graph of this, and we sketch the graph of that, and then we basically see where the intersections are going to be, and we can sort of use our geometric intuition to be able to work out some sort of a solution. Okay, so first of all, how do we sketch the graph of this? Well, this is very much in line with some of the examples we've seen so far, so you could just go and rewrite this in terms of piecewise functions, and that's fine, but in this case, just for fun, what I've done is I've done it using some sort of transformation. So what I've done is I've said 2x minus 1 can be factorized on the inside. So write 2 times by x minus a half in brackets. And then using this property, which we proved in one of the examples, I can actually take the 2 out and I can separate that with the x minus a half, right? And I'm going to have modulus signs in both cases. And the modulus of 2 is just 2. So in fact, the initial function that I had can actually be expressed in this sort of way. And if I define my f of x to be just b modulus of x, in other words, this thing here, right, then I can send my f of x to 2 times by f of x minus 2. And indeed, I've chosen this transformation because when this transformation is applied, you actually end up with exactly this thing here, right? So in other words, we can go from the graph of this to the graph of this by using this transformation, and we know that in this case we have to apply the thing that's happening on the inside first. So it's going to be a shift by a half to the right, and then it's going to be a stretch by a scale factor 2 on the y-axis. Okay, so the black graph here is the graph of my f of x, and then the blue graph here is actually carrying out this sort of shift to the right by a half, and then the red graph here is basically stretching each y value by 2. So in fact, we actually have the red graph as being the graph of our modulus function here. We then go and sketch the graph of y equals 3, which is this green line here. So perhaps I should just write that down. So y equals 3. And we can sort of see that we're going to get 2 solutions, right? So we're going to get a solution for sort of x value being bigger than a half, and we're going to get a solution for some negative x value effectively, right? And of course, the y value at both those points is just going to be 3. So effectively, it's a matter of solving this sort of graph simultaneously with this sort of graph, right? So I look carefully and I see, well, what's the equation of that chunk here? And you can sort of go away and think about this maybe, but the equation would basically come from that sort of expression. And because it's sort of for the positive x for x bigger than a half, then really it's just going to be 2x minus 1. And I want to solve that against y equals 3. So that's my first equation. And we can solve that to have x equals 2. And that's a really good solution because we see that actually our x solution is going to be more than a half, and 2 is certainly more than a half. So what we've had to do is we've had to solve the right branch of our modulus function, which is basically given by this equation here, which is valid for x being bigger than a half, with y equals 3, and we get one solution. Okay. Now we have to solve the left branch with y equals 3, and the left branch is going to have the equation given by this sort of expression here, right? So I'm going to set that thing here equals to minus 3, and that's another linear equation, and we can go and solve that linear equation, and we basically end up with x equals -1. And of course, we've already checked that these are actually the right solutions, okay? So this is one way to basically solve equations which are modulus equations, which is basically you sketch the graph of your modulus function, and then whatever other function you have, you sketch the graph of that, and then you start to see which branches are going to start to intersect. And then you would set up simultaneous equations for those specific branches, okay? Now, it's probably a good question to ask as to why is this a good way of doing things. In fact, this is my favorite way of solving modulus equations, and this is why. And the answer is here, because imagine if you've got some modulus function and you've got some other modulus function. So in these three cases, I've basically drawn two modulus functions. And where are they coming from? Well, they're coming from the fact that we might have something like ax plus b, and we might want to solve that being equal to, say, cx plus d. So we've basically got a modulus function on the left and we've got a modulus function on the right, okay? And when we go to plot these, depending on what our choice for A, B, C, and D are and so on, we might have things that look something like this to something like that to something like that. And the difficulty here is if you actually just applied the definition, you would find that the number of combinations of branches that you've actually got to consider to be able to solve the equation is actually going to be quite a bit. And what's even more worrying is solving some of those branches against some other branches is actually not going to give you the right solution. And there are reasons for why that is. What I'm trying to say is actually as follows. So imagine that we actually wanted to solve these two modulus functions simultaneously, right? Now, graphically, we can see that there's actually only going to be one solution, okay? But the point is, this has two branches, and that has two branches. So if you were to expand the equation for this out instead of piecewise description and the equation of this out in piecewise description and get all the various combinations of pieces equal to one another, you're going to end up with lots of equations, okay? And because there's only one solution, it doesn't really make any sense for you to be getting, five or six or four equations and then working out maybe five or six or four answers. And in most of those cases, you probably are going to get straight answers coming out. And the reason for that is because you're going to have a linear equation in each branch. So you're going to set up some linear equation to some other linear equation. And then when you do that, you're going to have a solution to a linear equation. But of course, that's completely sort of absurd. And the reason why it's absurd is as follows, because what you might actually work out for one of the branches is you might work out, say, this extension and that extension intersecting at some point here. And you might think to yourself that this is actually a solution, right? But the point is, this is not a solution because these sort of this part and that part is not really part of the modulus function. Whereas when you've just got the branch written out and you're not too careful about looking at what exactly the domain values are telling you and you equate the wrong sort of things, then these sort of outcomes can sort of happen very, very frequently. So we don't actually want to be doing any of this, okay? Instead, what we actually want to do is, from a graphical sort of point of view, get an idea for which branches are actually going to cross. And the minute that you know which branches are going to cross, you actually go to the description of the functions and you pick out those branches and then you set them equal to one another and you solve them simultaneously, right? So for example, let's take a look at this case. I might say this is, say, branch 1, and I might call this to be branch 2. And then in the blue case, I might say this is, say, branch 1, and I might say this is my branch 2. And straight away I know I actually have to solve the green branch 1 with the blue branch 1, and I have to solve the green branch 2 with the blue branch 2, right? So if I go away and solve, say, something like the blue branch 1 and the green branch 2, the solution I'm going to have is going to be something absurd. It's going to be something out here, because that's where these branches are actually going to intersect. And that's not a solution to our initial modulus equation, right? And a similar thing is going to happen if I actually go and solve branch 1 in green with a sort of branch 2 in blue, which is something like that. Okay, and again, this is not really a solution, so we don't actually want to be doing that. So I hope you can see already that actually having a sort of a graphical overview of what's happening is so much advantageous in being able to solve these things, right? And just so there are no misconceptions, you might think that the only cases we're going to have is we're going to have branch 1 and branch 1 being solved simultaneously, and branch 2 and branch 2 being solved simultaneously. And that's really not the case, because if I take a look at this case here, so I've got that as being my branch 2, and if I call this my branch 1 again for green, then what we actually see is actually in this case branch 2 green is actually intersecting with both branch 1 blue and branch 2 blue. Okay, so we've just got to be careful. So the best way forward generally is to basically sketch a graph of both the sort of modulus things you're looking at, and then see which branches are going to intersect, and then specifically go and solve those equations simultaneously. And when you're doing that, you can just treat them as regular mathematical equations. And of course, you get rid of the modulus signs. So the minute you go to talking about a specific branch, you don't really care about the modulus sign. Okay? So I hope you found that example useful, and I hope you appreciate the value of approach 1. Let's now go solve the exact same equation using approach 2. Approach 2 is the algebraic approach. A lot of students love this approach because it's so straightforward and you don't really have to do any thinking really. You just apply a method and the things just sort of fall out. And what you basically do is you start with the thing you actually want to solve, and you basically square both sides, right? And when you square both sides, you're going to have 2x minus 1 all squared on the left, and you're going to have 3 squared on the right. But we proved a result which said when you actually square a modulus, you can get rid of the modulus, right? So we can just drop the modulus signs, and those modulus signs can just be converted to regular brackets that we sort of know and love. And at this stage, it's basically just a case of solving this quadratic, right? So you expand this out. So when you expand this out, you sort of get this. And then obviously the 3 squared is 9, but then you want to take that to the other side. And you sort of get this quadratic here. And then, there's a factor of 4 basically in each term. So you divide through by 4. So you get x squared minus x minus 2, which can then be factorized. And you've basically got your two solutions, right? And we get the exact same solutions as we actually got before. And I'll sort of repeat again, we've already checked these already, so we know they're the right solutions. So that's approach 2. So let's now take a look at approach 3. And approach 3 is actually the direct approach, which is probably the one I would least recommend. But you can use this if you actually prefer. And the basic idea here is you apply the definition of the modulus function. Okay, so in this case, what I've done is obviously we want to solve 2x minus 1 equals 3. So I say that's the same thing as 3 equals 2x minus 1. I've just written it out in this way so that when it comes to sort of equating and setting branches equal to one another, it just looks slightly neater. So of course, the 2x minus 1 modulus can be written as 2x minus 1 for 2x minus 1 being sort of non-negative, and minus 2x minus 1 for 2x minus 1 being negative, right? And then you say, well, if this has to equal that, then 3 has to equal that for that x, and 3 has to equal that for that x, basically, right? And we can sort of set up two equations in this case, and we can go and solve these equations in each case. These are linear equations, so you're guaranteed to get solutions out. And in the first case, we get x equals 2, and in the second case, we actually get x equals minus 1, which is again consistent with what we've already worked out. And as I've already said, we've already checked that these are the right solutions. Okay, so just a word of caution as to why approach 3 is not always the best, and the reason why it's not always the best is suppose at this stage here, when you actually solve this, in some case you got something like x equals some number which is say less than a half. And that's going to be the worrying problem, right? Because if you were to get a number here for which you were told that x has to be less than a half, then actually your solution would not be valid. The reason why your solution would not be valid because this equality only holds for this condition. So if you were to then use this and then work your way down and get an answer such that the answer was telling you that is actually not going to satisfy that condition, then that answer and that condition are not sort of constructive, that they can't work together. They're mutually exclusive in some sense. And this is basically what was happening with approach 1 that we were looking at, where you can equate certain branches and then you can get a solution out, but that solution isn't actually a solution to the initial problem. So when you do use the direct approach, if you use the direct approach, just make sure that when you've actually solved something, and you've got a solution, that solution is actually consistent with the branch that you're working on. And of course, in this case, we want x to be more than a half, and 2 is more than a half, so we can actually come back and give ourselves a tick here. So that's completely fine. And of course, again, in the second case, we want the solution to be x being less than a half, and minus 1 is definitely less than a half. So again, this is sort of consistent here. So with that, you've actually seen three rather comprehensive ways of being able to solve modulus equations. There are lots of other ways, but I think it's sort of overkill to go into them now. So for now, what we're going to do is maybe look at another couple of examples, and then we can bring this video to an end. So example 7, we have another modulus equation, and in this case we have a modulus function being equal to a much more generic linear function. And I'm going to go with approach 1, and maybe we can check it using one of the other approaches. And in fact, as you can see, I've already done the graphs for both the thing on the left and the thing on the right. And the graph of x minus 4 modulus is very easy. It's just the modulus function shifted to the right by 4. And of course, we can also expand it and write out each branch explicitly, okay? The interesting thing to see in the graph actually is the fact that there's only one intersection. So you might expect that this line was going to cross both the branches, but actually it only crosses one of the branches, okay? So we only actually need to solve one equation, and we're going to have, say, if we call this branch 2 and we call this branch 1, we're going to solve branch 2 with the equation of this sort of purple line, and from here we can just see that this part here is going to be branch 1. How do I know this is branch 1? Because this is valid for x being bigger than 4, right? And we can see that if x is 4 there, then x bigger than 4 is actually branch 1. So the other one then has to be branch 2. So we solve branch 2 with 2x minus 1. So we say minus x minus 4 actually has to be equals to sort of 2x minus 1, and of course x better be less than 4 in this case, right? So when we just solve this, we just say minus x plus 4 has to be 2x minus 1, and we can just sort of rearrange this and just say 4 is equals to 2x plus x minus 1, which tells me that 4 plus 1 is actually going to be 3x, and indeed that's nothing other than the statement that x is 5 divided by 3. And of course the positive thing here is 5 divided by 3 is actually less than 4, right? Because this is actually less than 2, so it has to be less than 4. And that's again sensible because from our graph we actually see that we're going to get a positive x output or a positive x value, and it's actually going to be between sort of 0 and 4, and that's precisely what we have. We have something which is actually between 0 and 4. So we've actually been able to solve this. So let's check this, and perhaps we can check it using, say, method 2, approach 2, which is we want to be able to go from that to actually getting rid of the modular sign, and we can just do that by actually just squaring both sides. Okay, so we end up with something like this. And of course, the whole point of this is once I've actually taken the square of both sides, then I could just drop the modular signs. So I actually end up with something which looks a lot nicer. So now we expand this. The x minus 4 all squared is going to give me x squared, take away 8x plus 16. And the 2x minus 1 all squared is going to give me 4x squared plus 4x plus 1. Or rather minus 4x plus 1. Okay? So again, from here, we just sort of solve this as we would normally. Okay, so what I've basically done is I've taken the entire thing on the left here to the thing on the right. So the 4 minus 1 is going to give me the 3. The minus 4 plus 8 is going to give me the 4. And the 1 take away the 16 is going to give me the negative 15. And then we basically factorize this, which is fairly straightforward. So I've sort of done that here. And in fact, I knew that 5/3 was going to be a solution, so I knew that 3x minus 5 was actually going to be a factor, basically by the factor theorem, right? So therefore, the other one had to be just x minus 3 because the 3 and the 5 are going to multiply to give me the 15, okay? And of course, it actually should be plus because I actually want negative 15. So at this stage, we just say the solutions are going to be 3x minus 5 equals 0, or x plus 3 equals 0. And here's a slightly worrying thing now. We're actually getting two solutions. We're getting x equals 5 over 3, so that's fine. But then we're getting x equals minus 3. And that's clearly not fine because somehow we never got that before. So what's actually going on? So in fact, I picked this example precisely to highlight this, right? And what's happening is the same thing as what's happening here, which is the purple line is actually only intersecting my modulus function once, okay? Whereas the quadratic that you're solving is somehow actually solving also for this sort of thing here. So it's giving me a negative solution for something like there, which is obviously going to be something like -3, but we don't accept that solution. So what you actually need to do is if you are going to use approach 2, I didn't want to say this sort of in the previous screen, was because, or in the previous example rather, was because I thought it was too much information. So it's probably better to process this like this, which is when you do use approach 2, so when using approach 2, just check your answers afterwards. And you can now see why I prefer approach 1, because all this nonsense just seems to go away, okay? Whereas with approach 2 and approach 3, you can get things coming out where you actually have to go back and just make sure, is it sensible or not, right? So now let's take a look at the last example, and then we can basically bring this video to an end. Let's take a look at example 8. Given the length of the video, I've decided to just write a lot of stuff out in order to save time. So here we're required to solve the modulus of 3x plus 4 being equal to the modulus of x plus 5, okay? And we can see that, of course, we can get the graph for the modulus of x plus 5 by basically taking the graph for the modulus of x function and just shifting it to the left by 5 units. So that's the purple graph there. And the graph for the modulus of 3x plus 4, well, you can sort of think about this a little bit, and actually you can arrive at this. And indeed, if you put -4/3 into here, you would actually get 0. So you know that the key point at which the graph does a sort of a wedge is actually going to be at -4/3, and we also know that the two branches are basically going to be straight lines because we've got a straight line there. Okay, I've actually gone ahead and also labeled each of the branches, and I know that the labeling is sensible because if you take a look at this branch, for example, the gradient is positive, and if I go to the pieces, only one piece has positive gradient, so I know that has to be representing branch 1. So the other one has to be branch 2, and indeed branch 2 actually has a negative gradient, so that's sensible. And the same sort of reasoning can actually be applied here, and branch 1 again actually has a positive gradient, and branch 2 actually has a negative gradient. So we finally come to being able to solve this modulus equation, and we see that we're going to get two solutions. And indeed, we're just going to have the first branch from the purple graph actually intersecting with both the blue branches, right? So we're going to get two solutions. Solution 1 is going to be the blue branch 1 intersecting with purple branch 1. So let's basically solve this. Blue branch 1 is basically 3x plus 4, and purple branch 1 is basically x plus 5. So we can solve that, and we can basically say, well, if I take the x to the other side, I'm going to get 3x minus x, which is 2x. And if I take my 4 to the other side, I'm going to get 5 minus 4, which is actually 1. So actually x equals a half, so we already have a solution. And then in the second case, we're going to have obviously branch 2, which is here. So let me write that down. So it's going to be minus 3x plus 4. And that's going to intersect with branch 1 again, which is obviously just x plus 5, so I can write that down. And again, solving this, we can actually just say it's going to be minus 3x minus 4 is actually going to be x plus 5. So now taking the minus 3x to the right-hand side, I actually get 3x plus x is going to give me 4x. And taking that 5 to the left-hand side, I'm going to get minus 4 minus 5 is actually going to give me minus 9. Which actually tells me x is actually minus 9 over 4. So we've actually worked out the second solution as well. Let's do a quick sort of sanity check. So we look at this and we say, well, what is this valid for? Right? And we can sort of come back and we can say, well, we know we took branch 1 and we took branch 1. So it's actually valid for x being bigger than -4/3 and x being bigger than -5. So let's write that down. So it's valid for x being bigger than or equal to -4/3 and x being bigger than or equal to -5, right? But it's easy to see that actually of these two conditions, provided that x is bigger than or equals to -4/3 is satisfied, then the other one is automatically satisfied. So in other words, our solution better be more than -4/3, and our solution is indeed positive. So that makes perfect sense as to the fact that that's actually a solution, right? And again, our graph is reassuring from that point of view. We can basically come and repeat this way of thinking for this, and we can say, well, what is this valid for? So we can say it's valid for, so again, we're going to have the blue branch is now 2, so it's going to be x less than equals to, or x less than -4/3. And our purple branch is again the same, so it's just going to be x bigger than or equals to -5. Well, that's just the same thing as x being between, say, -5 and -4/3. And we can see directly from here that actually our solution is perfectly between -5 and -4/3. Indeed, -9/4 is just negative sort of 2 1/4. So we give ourselves a tick. With that, I'd like to bring this video to an end. I hope you found that useful. If you did, please hit the like and subscribe buttons. Do sort of say in the comment section as to what you would like to see more videos on. And as always, we will see you in the next video.